Alright, so next speaker is the Xiangbin Wang from Xiangbin Wang, who will give us talk about the making the decoy state TYQI2016 practically useful.
Okay, so good morning, everyone. Thank the organizer for inviting me here so that I can have a chance to report some of our recent results on the TYQI2016. Before I go into details, I would like to first introduce the major contents of my talk. What I want to say is that, in practice, given the practical existing setup, if you want to really make a secure quantum key distribution, it's not an easy task. If we go back to the initial security proof of short press-cures type, which requires the single photon source, the perfect single photon source, and also if we consider if there is no perfect single photon source, then you may use the well-known photon number splitting attack. So we need the decoy state method. If we implement the decoy state method in practical setup, that's still not enough, because as we all know that there is a famous paper given Markov et al. Said that if there is a channel loss or detector loss or detection loss, then Eve can always, on the one hand, pretend her action to be the channel loss, on the other hand, to control the instantaneous detection efficiency, then to completely attack the protocol. In that case, we also need the TYQI2016, that's the measurement device independent quantum key distribution. However, the major drawback of that is, of course, if we don't consider the finite size effect, that works very well. The secure distance can be even longer than the traditional BBA default. However, if we consider the finite size effect, the efficiency of the decoy state TYQI2016 is rather limited. If we want that to be really practically useful, we should try whatever we can do to improve the efficiency, to improve the period, to improve the distance, so that it can produce a meaningful final period for the practical use. In this talk, I will introduce one of our recent work on how to hugely improve the period in the case of small data size. Okay, that will be the major goal of this talk. Before going to that, we need to start from the. I would like to start from the very beginning. This is the outline of my talk. I will first introduce some background knowledge of BBA default and the practical security issue, the decoy state method, and the decoy state plus TYQI2016 and its optimization. And finally, I will introduce our method, which is a full intensity decoy state method, TYQI2016, and its optimization. And then, since there is an experiment recently, I will also introduce some major results of the experiment. Okay, let's very fast go through this. This is the BBA default. And we need the key distillation to obtain the secure final key. However, there are some practical issues, such as the security proof relied on the perfect single photon source. It didn't consider the channel loss, and also it didn't consider the detection limitations. Okay, for example, consider the practical setup. We normally we use the easiest source, that is the coherent light source. This which is a distribution of different photon numbers. in such a way, there is a so-called photon number splitting attack. It can make this scheme completely unsecure, or if the distance is long, say the secure distance is less than 20 kilometers. Sorry, this is an estimated value given the detector technologies at that time. 10 years ago. Okay. Then, in such a case, we need if we use an imperfect single photon source, we can use the ILM GLP result for the task. However, this delta is unknown, but this can be estimated very tightly by using the decoy state method. That's the purpose of decoy state method. Say, if you have a way to tightly estimate this delta, then you can use such type of. There are a lot of improved formulas. You can use such type of formulas to obtain a considerable final tip. Then the decoy state method. With the decoy state method, we can do that task. The method is very simple. Just say we switch intensities among a few different values. Okay. Then by observing the counting rate of each intensity, we can do the calculation. However, if we implement the decoy state method, we can do secure quantum key distribution with an imperfect single photon source. However, there are other loopholes. Okay. Initially, we assume that Eve can completely control the channel, but cannot attack inside Alice Bob's lab. However, in practice, this seems not to be the case. Actually, Eve can attack the detectors. Okay. So when there are channel loss or detection loss, then it's still unsecure, given such type of detection attack. To overcome this difficulty, we need this MDI-QKD, which is proposed by Lowe and Bronstein. I had better not to introduce the very detail of this. Okay, roughly speaking, that Alice and Bob from each side they send a pulse, and then in the middle measurement station they take a Bell measurement. Of course, we don't have perfect Bell measurement, but we can use beam splitters to take partial Bell measurement. Well, this is a very good idea. Then, with this idea, then we consider the issue in this way. We use decoy state method plus this MDI-QKD. Okay, then we can avoid all attacks. We can, on the one hand, we can use imperfect single photon source. On the other hand, we don't worry about the channel loss attack. However, the key rate, that's the major problem. Okay. When we use decoy state method plus MDI-QKD, if we only consider the asymptotic key rate, that's okay. It's quite good. It's quite good. However, if we consider the finite size effect, okay, for example, consider this paper. Okay, we can treat the finite size effect very well. However, the key rate is not so good, especially in this figure. In this picture, for example, consider this curve. It assumed a total number of pulses of 10 to 12. Okay. the Q rate itself is not so large, and also on the other hand, if we use a smaller data size, then the Q rate becomes smaller and smaller. Can hardly be really used in practice. I mean, suppose we want to use the fresh key. Okay, we want to use the fresh key. We pick up a phone call. Then we wait. We wait for the generation of this final key. But we cannot wait for too long. Maybe we can wait for a few minutes. Okay, but we cannot wait for a time, say for example 1 hour. That's impossible. So our task is, can we make a meaningfully high key rate with a very with not so large number of total passes? Okay, with not so large data size. The answer is yes. But let's consider some background towards improve the key rate. There is a systematic work by Xu Hu and Lou. They said that they reported a very nice result that of global optimization. Say in the decoy state MDI-QKD, there are a lot of parameters we need to set in the experiment. Say the properties of using each intensities, and also the intensities of each type of pulse. Okay. Then in their work, they optimized all parameters to make the full optimization of this. From this, we can see that the key rate has been indeed improved a lot. Okay, this is a logarithm picture. This gap is actually quite large. This gap is actually quite large, say 1 to 2 magnitude orders. Okay. However, this is still not sufficient, because this has made a large step towards improving improving the efficiency, but it still needs requires quite a large amount of total number of pulses. Okay, then the question is how to further improve the efficiency. Okay, that will be our work. We shall take two steps. First, we use more tightened calculations for the final size for the key rate. And second, we change the protocol for the decoy state part. We will instead of using the symmetric protocol, which produce the same thing in X basis and Z basis, we use asymmetric protocol. We use 4 intensities in all. First, let's show one type of more economic, more tightened calculation. So we in treating the statistical fluctuation, actually we use a lot of we use some constraints. We use some constraints to figure out the say for the upper bound of the single photon, the yield of single photon pairs. Sorry, the lower bound of the yield of the single photon pairs and the upper bound of the single photon pairs phase flip error rate. Okay. In principle, previously, so the number of constraints, we just use the constraints like this. Whenever there is a different intensity, then we list a different equation. So how many intensities used in the protocol means how many constraints. However, if we think about the issue carefully, we can also just regard the different sources of different intensities. We just regard them as one complex source and list some more constraints. That's what we call as we use a joint constraints. In the protocol, there are many many situations for different intensities. For example, for this side gives intensity 1, that side gives intensity 2, and so on. If we consider all, when we say we need to use joint constraints, although there are a lot of joint constraints, however, the actual calculation shows that we only need a few of them. So this picture shows the key rate. The upper line is the key rate of using joint constraints. There are two curves of the upper line. One is orange one. The other is a dashed line. These two curves are corresponding to the case that we only use a few of the joint constraints, and we use all the 500 joint constraints. They are almost the same. Okay, this blue dashed line is a key rate given by Xu Fei Wu. So in this curve, we find that if we consider the joint constraint alone, it will improve the key rate, somehow improve the key rate. Then we find that improve the key rate by more than 100%. However, this is still not enough. Okay, this is still not enough. We want to hugely improve the key rate, especially in the case of small data size. Then there is a method. We call it as the optimized full intensity protocol for this goal. This can improve the key rate a lot. Say improve the key rate by 1 to 2 magnitude orders. The protocol itself is very simple. It's just a type of decoy state method, but slightly changed in the intensity arrangement. We use 4 sources at each side. These 4 sources are vacuum source, say O, weak source in X basis, say X, strong source in X basis, say Y, and the singular source in Z basis. This means that in Z basis, we only use 1 source as a singular source for key distillation. And we shall take optimization for probabilities of intensity of each source. But this is not the only thing we have done. Okay, so we also take some more tightened calculations. Besides this different protocol, we also take some more tightened calculation. The joint constraint is one of them. Okay, consider we say that each side we use 4 sources. Here we listed 3 of them, 3 non-vacuum sources. Another one is a vacuum. Well, besides the joint constraints, we should also consider the yield of single photon pairs, say S11, and the phase flip error rate of single photon pairs. We treat them jointly. Okay, we treat them jointly. How to say? Both of them are actually a functional of the vacuum count. Okay, say here is the formula for that. Say the upper bound of the phase flip error rate is a functional of the vacuum count here. Okay, and the lower bound. The lower bound of single photon pairs yield is also a functional of this. Okay, in the past we choose the worst case like this. We choose 2-step worst case. First, in calculating this value, we consider the worst case for this parameter. We use the largest possible value of this. Then, in calculating this, we use the smallest value for this. Okay, this result is correct and secure. However, it's not economic. So here we treat it like this. We say this is a parameter. We are not sure the exact value of this parameter. However, there is one value. Okay. Then we consider the final keyword formula. We just exhaust all possible values for this, and consider the worst case result for the final key only. We don't have to consider the worst case result separately. Okay, that's another difference in our calculation. In the formula form, we take the final keyword by this formula. So we scan all the vacuum count, all possible values for vacuum count in its set. Okay, then we take the worst case result of the keyword. Okay, here I list some of the numerical simulations. So this is a calculation for the total number of pulses of 10 to 10. Okay, this is the curve calculated by Yu et al. Paper. This is given by Feihu, and this is our latest result. So we find that indeed, first it works. It works with the small data size, and also it has a very large rest in the keyword. Okay. So because the time is rather limited, I don't want to list all. I don't want to list all of our calculation results. In the last few minutes, I want to introduce a very recent experiment. Given this, the experiment has been done already in USDC by the group led by Xiangbin Wang. Here is the major result of the experiment. First, instead of a proof of principle experiment, in this USDC experiment, we fully implement the decoy state method through randomly switching the intensity of each pulses. Okay, this is very important. If you don't do this, then it is actually not secure. Second, we obtain a result of secure distance over secure distance of 4 and 4 kilometers. But this is in the ultra-low loss optical fiber. Second, we obtain a result over a secure distance of 311 kilometers. This is using normal optical fiber. Thirdly, we redo the experiment of 207 kilometers. Period is improved by more than 500 times. Among them, about 50 times are from the method, our fault injection method, and another 10 times are from the improvement of instruments. Lastly, we reached a distance which is not accessible by traditional BBI-84 protocol, even with a perfect single photon source. Okay, so this is because we use the MDI scheme. Okay. This means that we actually we have beaten a quantum limit of perfect single photon source through using imperfect single photon source. In summary, we presented the best known theoretical and experimental results for the decoy state MDI QTID. These results indicate that the method can have a meaningful efficiency for practical use. Thank you very much.
Questions? We have time for any questions. Maybe we can have after you have next speaker set up the and then okay, then let's thank the speaker again.